Hi, in the previous video, I explained the identification. Now I'm going to show you how to implement the GMM, optimal GMM. Basically, this means optimal GMM means how to choose weight matrix W. Okay, I'll explain that. And like in here today, I'm going to use just the standard one, non-demeaned method. Here, demeaned method and non-demeaned method does not make much difference because we don't need to check invariability. So we will consider the full model HI plus. Okay, you remember here the error term includes the measurement error. So we have to think about this. And our moment conditions can be written as mi theta. Remember theta, where theta is alpha, beta, gamma, and I will define x to include all the regressor constant L, H, and Zi is 1 and Li and Gi. Okay, so then under these notations, we are going to use moment function of this form, right? And then we know that expectation of mi theta 0 is 0. Okay, that is our moment conditions, right? So based on this is just theoretical derivation, and here like from your data, what we are going to do is we are going to minimize over theta in a parameter space big theta, and we will think about this W, this. The sample moment function is weighted by W. Okay. So then you may check the dimension, by the way. Z is, so it's 3 by 1, it's 3 by 1, everything is 3 by 1. So it is 3 by 1, it is 1 by 1, it is 1 by 3, it is 3 by 1. So M is 3 by 1 function, valued function, factor valued function, and 0 is of course 3 by 1. And that means this function is 1 by 3 after transposition here, and this is 3 by 1. So W should be 3 by 3, right? So if you can choose the correct W, then you can minimize. Minimization is not a problem, that is just a computational issue. And what I'm asking you here is how to choose the correct weight matrix here. And there are several possible answers. Simplest answer, so version 1, correct answer version 1. Simplest and I would say most clever answer I expected is the number of unknowns equals the number of equations, moment conditions. So weight matrix W does not matter. This is the most clever answer and correct answer, right? It does not matter. Like anyhow, whatever you choose W, it will be the same minimization, right? So let's use identity matrix, the identity matrix as the weight. This is the best answer, simplest answer. Actually, the question is pretty simple. The next second best answer is for optimal GMM, we learned the weight matrix W must be proportional to omega inverse, where omega is the variance of moment function at the true parameter value. Okay. And We know, you know how to derive it. It looks like this, okay? And then in the question, I did not copy that. In the question, I told you epsilon is statistically independent of z, right? So statistically independent is very strong. It already implies the conditional distribution of epsilon given zi does not depend on zi, which means, which implies the variance of epsilon conditional on zi does not depend on zi. So automatically implies homoscedasticity. Same thing, I also assumed ui is independent of z, which also implies homoscedasticity for ui. So if we just define sigma squared as expectation of epsilon I minus gamma 0 ui squared conditional on zi, then omega becomes sigma squared times expectation zi transpose. Okay, so we need W to be proportional to this guy, but it is proportional, like in class I said as if W should be omega inverse, but at the time I explained that the positive constant does not matter in the minimization problem, so we just need W be proportional to this part, which is easy. So I suggest you can use W as the sample average of z prime inverse, right? So instead of the expectation, I use sample average and then just take its inverse. That is the second best way to implement the optimal GMM. But as I said, even if you use this, the solution should be the same as the simpler version, right? They don't have any difference in the sample in your implementation. And the worst, like not worst, it's still correct, but not so clever answer is two-step GMM. So we start from here, say epsilon I minus gamma 0 ui squared zi transpose. We wanted to, if you want to estimate this, then as always, this is a problem. Expectation should be replaced to sample average, and additional problem is epsilon is unknown, u is unknown, gamma 0 is unknown before estimation. So we are preparing to implement the estimation. So this part is the main problem. How do we solve that? The idea is they are coming from here. Okay, so what we want to do here is we would like to estimate this part using, say, suppose that preliminary theta tilde, define theta tilde as be the minimizer arg mean theta over the same thing, transpose W. Here I can use any W, so let's use the identity. Whatever W you may use. So use any weight will yield a consistent estimator. This will be consistent for any weighting matrix. Even if it is any weighting matrix means like still it should be strictly positive definite and symmetric. So any weighting matrix that satisfies the minimum assumption will yield consistent estimator theta tilde, and then I will calculate yi minus xi prime theta tilde. The preliminary estimator will give you something like this, right? So the residual from this one, like assuming that theta is consistent, if theta was consistent, basically I am estimating this part, right? So we will obtain the residual, which is theta minus gamma u, right? So we can calculate this residual. So we calculate you may calculate, so plug that in here, and then you can calculate excuse me, I will be more exact to be more precise. You may calculate something like this as an estimator for omega, and then your weight matrix can be its inverse. Then this is also reasonable way to estimate the GMM estimator, but as I said already, this is optimal. So you are going to get, if you use this weighting matrix and get theta hat, this will be the same as this one, because we have same number of unknowns and the same number of equations. That's how you can do it. And next question. Next, you can derive the asymptotic variance for the GMM estimator. Discuss how you estimate the asymptotic variance in finite sample. So, we are using optimal GMM. Then we know asymptotic variance was G transpose omega inverse G inverse. This was the asymptotic variance, and at that time, like we know, G was the expectation of derivative moment function, like this, if you remember, right? And in our case, it is pretty simple. It was minus, say, zi xi transpose. Okay, right? Well, it was linear in theta, so differentiation with respect to theta is pretty simple. And earlier we learned omega was expectation of epsilon I minus gamma 0 ui squared zi transpose, right? Now we just need to calculate how to calculate. Again, let's see what are the problems in our these are the theoretical result, but in practice, what is a problem? The problem is these expectations, right? But it is easy. We just replace expectation with sample average. That's simple. And another problem is this one, right? This error term is unobserved, but not a problem. We are going to use the same idea as this one. This one, like we use this idea, but the difference here is in our previous argument here, it was preliminary step, because we calculated this to calculate the weighting matrix, and weighting matrix must be set before calculating theta. So we had to use a separate theta to calculate the weighting matrix, but here we are calculating variance, which comes after the main estimation, right? So simply you may estimate this part as yi minus xi prime theta hat. that's sufficient. Okay, so then pretty simple. So this is the main estimator, second stage, or the final estimator. So use g hat, define g hat as minus, we may ignore minus this like this, and omega hat as 1 over n this. Okay, and then you can calculate that, right? It's all about data and your estimator. So it's your data, 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 and this is your estimator. You already calculated the estimator, and just summation, right? So you can calculate everything here, and then calculate just g hat transpose omega hat inverse g hat, and their total inverse will estimate your asymptotic variance. Okay, so yeah, I will stop here and I'm going to continue the final question in the next video. Thanks for watching.